Hello and welcome to the 12th episode of Delving into Academics. For those who are new here, it's a podcast where various researchers from physics, chemistry and biology are interviewed about what they're currently working on and also their life as an academic. In this episode, Dr. Jenny Smillie is interviewed about her work on the accuracy of theoretical predictions for LHC collisions. I hope you like learning about the more theoretical side to the LHC, and I hope you enjoy this episode. So today I'm here with Dr. Jenny Smillie. She studied at the University of Cambridge for a bachelor's in maths. Then she went on to do a PhD at the University of Cambridge in physics. She then went on to do work at Durham University, at the University College of London, and finally at the University of Edinburgh. Welcome to the podcast. It's so nice to have you.
Thank you very much.
So why don't we get started with you telling us a bit about what you're researching currently and go from there.
Okay, so I'm a theoretical particle physicist, so I work in physics, but my main work has a very high amount of maths in it. I don't do any kind of practical experiments, but instead I calculate what experiments should see. So the particular focus of my research at the moment is on the Large Hadron Collider. That's the massive experiment at CERN in Switzerland, where they found the Higgs boson in 2012, and they're continuing to look for new particles and to answer many of the questions we still have about physics. It's an incredibly impressive machine. It's a very powerful machine with a huge potential, but because it gives us so much capacity to go beyond what we've explored before, it also is a big challenge for us on the theory side to actually make accurate predictions for what we expect to see. And if we can't do that accurately, we can't decide if we've seen the expected or the unexpected. And so I've worked on different things at different points in my career, but at the moment I work with the particles we know about. They're known collectively as the Standard Model, and I'm trying to make the most accurate predictions that we can for the LHC of how we expect them to behave. So with the ultimate aim of seeing if we can pick out anything unexpected or anything new at these new energies.
No, wow, that sounds fascinating, and I have to say particle physics is a big passion of mine, and so I just love learning about it and seeing where it can be developed. So I was wondering, how do you go about making theoretical predictions and making them more accurate as well? How do you know that you're making a prediction accurate if you don't necessarily have the result?
It's a very good question. Within a particular model, there are different ways of deciding or measuring the accuracy of your prediction, let's say. So if actually all the particles we know about genuinely are the only particles that exist, then we know what the final answer should be. The problem is that we do not have powerful enough computers, we do not have smart enough techniques to do the exact answer. So we have to make approximations using something that we call perturbation theory. And in practice that means you make as many approximations as you can to get something, the roughest prediction you can, and then you refine that by adding corrections. Usually you measure the terms in the coupling, which is just a parameter in the theory. It's just a number, but it tells you roughly how many approximations or how few approximations you're making. And one approach is to do, say, the lowest order. So maybe if your parameter is alpha, then you can say I can get everything that has an alpha squared, but I don't have anything that's alpha cubed or alpha to the 4 or alpha to the 5th. And that's been the standard approach, and that has worked very well for many different things, certainly for previous colliders. And the idea is that your alpha should be small, so the things you don't have are small compared to the things you do. And you actually know how big alpha is, so you can say, is that a 10% correction or a 1% correction, or you can measure it like that. And the more powers that you calculate, the more terms in your series you calculate, the better your approximation should be. At the LHC, one of the challenges we have is that although alpha is small, the number multiplying the alpha is not necessarily small. Each one can come with a big log, and so your whole approach breaks down at that point. If the terms that are like the sixth term in your series is actually the same size as your first, it doesn't make sense to stop. You can't approximate 1 plus 1 plus 1 plus 1 plus 1 plus 1 by just taking the first term, which is 1. And so it's a new problem at the LHC because there's so much energy. Because the centre of mass energy is so much higher, then each alpha has a log that multiplies it, and it's a log which is proportional to the centre of mass energy. And then because that's suddenly so big, you're taking a log of a big number and multiplying that by alpha is not small. So that got quite mathematical, but what I try and do is to be systematic about expanding in alpha times log instead of being systematic about expanding just in alpha. So it's a new approach to an old problem of how you make the approximations to describe the collisions.
Don't worry about getting mathematical. It's so interesting to see where maths can be used, because so often we're just kind of given equations and then we're kind of just been like, oh, let's memorize this and just use it in a random problem. But it's interesting to see its applications in the real world.
Well, yeah, and actually there have been new branches of maths which have come out of the way we're trying to calculate. The types of calculations we need to do, and by need I mean we've got data from the LHC and we need to make a theory prediction to match it. Those calculations require us to be smart, and they require us to find new mathematical techniques, and along the way we have actually learned about some pure mathematical areas and developments that have come out of it. And at the moment there's a big community within physics called the amplitude community, where the amplitude is the probability of something happening, and to calculate the state of the art amplitudes then there's people who actually collaborate directly with pure mathematicians, and there's input and output on both sides. It's very much a two-way thing, and the line between physics and maths is very blurred. It's not a clear division.
So then you kind of mentioned like one aspect that has come from doing this type of research with the pure mathematics and how that's been developed through this. Has there been any other areas that have been developed, theoretical predictions made from this?
It depends. The exact theory stuff, I would say the big developments have come probably on the data side. We work closely, people in Edinburgh, not me personally, but people in Edinburgh work closely with Intel and IBM in chip design and stuff, because really we are pushing the limits. The LHC pushed a lot of limits in what could be built. It's the strongest man-made magnetic field and things like that. But equally, the calculations, we're always pushing the boundaries of what is possible to calculate with the tools that we actually have. And most of the predictions made nowadays could not have been done 10 or 15 years ago. We didn't have the computing capacity, or the methods. There have been a lot of developments on the data side, and Peter Boyle in Edinburgh, for example, works with Intel and chip design and things like that, really hardcoring how can we improve the performance of computers. And that is motivated and pushed by what we need as a theoretical physics community. There are huge spin-offs from the experimental side as well. The technology side is enormous. And again, it's not what I work on, but there are brilliant things. There's the Medipix collaboration, who are making artificial retinas from people from the technology used to make a particle detector. I mean, it's the same thing. What you need to see is to detect a photon to detect light. That's how we see things. So you would need to detect photons very accurately in a particle detector, and that same technology has been used to make somebody an artificial retina, for example. The output from the experimental side is huge. And then there's the World Wide Web, that came from CERN, to share information. Now, we hear about that all the time, but we shouldn't forget that, that it's very important. And one of the strengths of our field is that people are doing this for the sake of knowledge and the pursuit of knowledge. And it changes things very much. If the World Wide Web had been developed in a commercial environment, if it was Apple or Google or Microsoft who did it, then we would all be paying a penny for every email or something. But anybody can send an email. Everything is free because it came out of this knowledge-driven sector.
Yeah, exactly. And I do agree with you there. I love what can come out of just that thirst for knowledge that researchers have, just to go beyond the limits and just keep on pushing them. What has driven you to become a theoretical particle physicist?
It was a slightly indirect route, actually. I've always envied people who know exactly what they want to do and have done it. That must be a very sort of straightforward way. It's never been as straightforward for me. At every stage, I have always sort of had to think long and hard about what the next stage will be. So probably the point which was clearest to me, I think, for longest, was that I wanted to do maths at university. Right from primary school, certainly through secondary school, standard grades, hires, SYS as it was then, now advanced higher, all the way through that, maths was the thing that I enjoyed the most. And the more sort of advanced the material got, the more I sort of really thrived on that. And I had no idea what I wanted to do with the maths afterwards. I knew I wanted to keep doing maths. And my school suggested that I should consider Cambridge. I was the first person from my school to do undergrad at Cambridge. I think somebody had done a master's before. And I applied for it, not really expecting to get in, to be honest, and not even sure if I really wanted to. I was just kind of a stubborn enough teenager. I wanted to know if I could. That was really my driver for it. And then once I got in and visited, got into the application procedure, and visited and applied and was interviewed, then I knew I did want to do it. And so in the end, I got there and I did do my maths, and I really enjoyed it, but I fully intended to do my 3 years in England. It's just a 3-year BA and come back. I've always been quite a sort of home bird. I didn't go to Cambridge because I wanted to go far from home. I went because that's where Cambridge was, and I always planned to come back. And I met an architecture student in Freshers Week and their course is 7 years. And I said to my mum, wouldn't that be awful? Imagine starting 7 years, down here. And I did 7 years in the end. But there you go, never say never. But and even then, I think it was probably fairly clear to me I wanted to do the extra 1 year masters to make it a master's degree. From partway through second year, certainly in third year, I didn't really doubt. It was called part 3 of the tripos. It felt like it would be incomplete to me to leave before that. And so I knew I wanted to do that, but the decision to do a PhD really wasn't clear to me either. I looked at various options, I thought about various things. I think I let myself be a bit put off by people who from the first day of undergrad said they wanted to do a PhD. And because I hadn't felt it as strongly as that right from the beginning, I somehow thought that ruled me out, which is obviously nonsense. It doesn't matter at all, and the more variety and diversity we have in people studying at an advanced level, the better. But the final decision for me was about November of my master's year, when I was sitting working through some tutorial sheet, and I thought, actually, I'm really enjoying this. I'm not ready to stop learning the new material. And so finally that was a kind of moment of clarity for me to carry on. Then I had to decide actually exactly where to apply, and I spent my Christmas holidays visiting loads of different departments, talking to people. My director of studies gave me names of people in different places in Scotland and in England. I went and visited. I spoke to my own director of studies, who said, what is it that which part of which course of that particularly speaks to you, if you like. And I said, the thing that I thought was brilliant was in symmetries in particle physics, where we did all this really complicated group theory, And then they suddenly said this is the measured particle spectrum. This is the spectrum of the mesons that you can measure, and it came out exactly out of the group theory, and I was just blown away by that, and still am at some level. And when I told him that, his face kind of fell, and he said, "I think you should go to the physics department." And it was a brilliant decision for me. I approached Brian Webber, who was head of the theoretical particle physics group in Cambridge. I applied there, I was interviewed there, and ended up being his student, and I think it was a very good fit for me, actually. That it matched, like I said at the beginning, most of what I do is maths, but it is motivated by data and actually what we can measure and see. So it has this, it's very advanced maths, but with a connection to the real world. So, as I say, it wasn't straightforward, but that's how I got here.
Yeah, no, that's really interesting to hear that you didn't really think you'd be doing a PhD at the beginning or even a master's, but somehow it just kind of all fell into place.
Yeah, exactly. And if you'd asked me, even if you had persuaded me at the start of first year, or like before I started my undergrad, that I definitely would do a PhD, then I would, at that point, I would have told you that, alright, the most likely area, my favourite area is pure maths. And it just sort of, again, it evolved as my degree went on. I moved away from the pure maths and more into the physics side of maths. They have a lot of physics courses, as we do here. We have a lot of sort of physics courses within maths, in this grey area, all the quantum stuff, all that stuff. I did, and ended up taking the line of quantum field theory and particles.
Yeah, that's quite cool. So what interests you so much about this connection of maths to the real world?
I don't really know, to be honest. It's kind of hard to explain. I've always enjoyed maths for maths' sake as well. And I mean, I am the sort of person who enjoys spending ages over a maths puzzle just because it's a nice puzzle, and there might be a neat way to solve this, or who would have thought you could get this solution, or how do you solve this. I think I had maybe got a bit used to thinking of maths like that. I knew there were things like mechanics and stuff like that, where obviously an engineering, which is a much more practical application of maths to everyday life and to everybody's everyday life. But I just hadn't realised that the more sort of technical abstract stuff like groups actually also can then give you a number you can measure. It was just really, I was shocked by it the first time I learned it, and I'm still amazed by it, and love the fact that the very, very technical maths that we can do actually matters. There is a motivation and a reason for it.
Yeah, it's awesome to hear that you've continued your passion after all these years, and you just sound so passionate about maths, and your love for maths is just coming through. It's so great to hear.
I think that's true. If you catch me on a day when I've been debugging for a week or something, then I'm perhaps a little less enthusiastic about it. That's the same in any research,
Yeah.
And I think people are always driven by the big questions, and that is what keeps you going through the day-to-day stuff, which is much more mundane. Day to day you're not actually discovering something new. You can't discover something new every single day, but you have to keep going through the calculation and through the hurdles and through the numerics and stuff to get that result.
Yeah, exactly. So kind of following on from that, like, what's your favourite thing about being a researcher? Is it chasing those big questions and to go through those calculations to get to that final result that you can then
I think so, yeah. I mean, being a researcher is it's a privilege in many ways because you have so much freedom. I'm not paid by the university. I'm jointly paid by the Royal Society and the European Research Council, and they really put a lot of faith in me. They give me money and trust me to go off and to spend it. That pays my salary, and it's not a vast salary, not like you get in investment banking or something, but it's a comfortable salary just to spend my days trying to answer questions that nobody can answer. And that it's a real privilege to be trusted to do that, and to give a return for that money, you know, to face these questions. I mean, they don't give it lightly. You have to prove that you've got an idea. You have to prove that you have the skills and the ability to do this sort of thing. But, you know, day to day, I have a tremendous amount of freedom in how I spend my day. I don't have somebody checking how much I've done every hour or something like that. And that's something that I think none of us should actually take for granted, that it is a very fortunate feature of being a researcher.
I mean, that sounds bliss. Like, just spending your days researching a topic that you love, like.
Well, actually, you know, it sounds like bliss. It's not always bliss, isn't it? By the nature of research, I mean, you can spend a week working very, very hard, thinking very, very hard, and realise that you're getting nowhere, and you have to give that up and start again. And that can be quite hard to do. So yeah, you do have the freedom, but there aren't kind of easy wins. I don't know, if you think there's like at different points of our year we're teaching, for example, and we have to say mark exams. Now, marking exams is not particularly exciting. It's not like having the freedom to come in and think, what will I try and solve today? But I know that if I spend an hour marking exams, by the end of that hour I can tell you, today I have achieved grading these scripts.
Yeah.
Whereas with research you can go weeks and months without being able to say, I have achieved this today. And I mean, you know you're working hard, you know you're tackling the problem, you know you're trying something new, but you may not get something back for it. And that is the downside of the life of a researcher. And you have to keep your motivation going to keep going through those times.
Yeah, that's kind of interesting to see then, like, I guess the flip side, because very often people are like always looking at the positive whenever they describe their job. So it's kind of interesting to then have that flip side and be like, oh, okay, well, this is what you have to deal with as well. Like, you kind of have to deal with both things.
I don't believe that it actually is a completely perfect job. I mean, there are obviously some that are better than others, but, you know, there's always flip sides to everything. You know, another advantage of being a researcher is we have a lot of flexibility. We have a lot of control over our working hours, for example. Mm-hmm. I have 2 small children, and if one of them's ill or something, then it's usually fairly straightforward for me to rearrange my day and be at home to look after them or whatever. But the flip side of the flexibility day to day we have is that there's also an expectation that we're always around. You know, because nobody's there saying, are you working between 9 and 5 sitting at your desk in your office, which would not be a sensible thing to try to force research into. And companies like Google and stuff recognise that. They've changed their offices to kind of reflect that. But because of that, there is an expectation that somebody can email me at 10 o'clock at night and I will reply. There is an expectation that somebody can email on Saturday morning asking me to do something by Monday and it will be done. You know, you're never, because you don't have the fixed hours, you get the flexibility, but you're never off. So it's like I say, there's ups and downs, and it's, I mean, it comes out on the pro side, I think, but it's not. It would be wrong to pretend it was some sort of ideal setup, you know, some sort of perfect thing.
Yeah, it's nice to get a real image of what being a researcher is like. That's kind of why I started this podcast, because I feel like we don't really get the full picture of what life as a researcher is like.
I mean, it's true that because usually students interact with us just through our lecture courses, then I think it's natural for students to see us as lecturers and see, but actually that's quite a small fraction of our job. If you average over the whole year, you know, term time is 2 11-week terms is about half the year, and also during those terms we're not exclusively doing teaching, we're also carrying on with our research and the other parts of our jobs. So it's actually for us it's quite a small fraction of what we do.
Yeah, exactly. So kind of moving on, I did want to ask you about any advice you have for undergrads. So they kind of only see this lecture side of the professors and researchers. Do you have any advice for anyone in undergraduate degree who maybe is looking into becoming a researcher? Kind of like maybe what they can do, or any just tips to being an undergraduate?
I think when it comes to sort of trying to decide where you go to the future, I think you shouldn't underestimate how long you should think about it. I think you should think seriously about it. I don't think you should make the mistake I did of being kind of put off by people who seem to know exactly what they want to do. Whether that's a PhD, whether that's banking, whether that's teaching, you know, even if you don't have a clear idea, that doesn't mean you can't do it. You know, you don't need to have been born to knowing you know to do that. So I think you should be open-minded about all your options, and I think you should think about your options and use your summers wisely. I had summer jobs every summer between my undergrads. They were very varied. I worked in a doctor's surgery on the reception. I worked at what was BAE Systems, and I did an academic research project as well. And certainly, and here in Edinburgh, you've got lots of opportunity to do that. There are industry projects and academic projects funded with bursaries over the summer. And having done the different things helped me to better have an idea of what options there were and where I saw myself and what I liked in a job and what I didn't. And I actually enjoyed all of my summer jobs, which is also something, you know, it was useful to know later on that actually I think I could be satisfied in a number of different careers. And that's also something that's good to know. But I think because there are a lot of projects within the university, increasingly, at least from students I've spoken to, increasingly students are doing, say, 2 or 3 different research projects within the university. But the truth is you're also doing your MPhil project and your senior honours project and stuff. It doesn't add that much. And maybe do one, but I would definitely say go and try and do something different in your other summers. There are companies who will offer summer placements. There are some who offer industry placements through the School of Physics. Ross Galloway organises them. And it's just a great opportunity for you to try out different things. And even if you hate it, then when you come to make your decision, you know that you don't like a job that includes this thing or something, you know, this particular thing. I think that's quite important.
Yeah, no, that's great advice, because I feel like some people, or at least for me, definitely I'm very much closed-minded to various options. I tend to shy away from trying new things, so or I might not think that they would be important in the future, but you're absolutely right that maybe trying that new thing, I actually find that I'm more passionate about this than I was about anything else. So
yeah, and you've got nothing to lose if it's a summer project. I mean, it's 10 weeks. I mean,
yeah, exactly.
even if you, as I say, even if you don't enjoy it, it's unlikely you're going to hate all of it. There probably will be some aspect you like, even if you don't like the whole thing. Yeah. And even if you dislike the whole thing, that's something that's helpful for you to know for the future. So there's literally nothing to lose, I would say.
Yeah, absolutely. So I guess the final thing is to tell us your inspirational book/article and kind of just explain what how they inspired you.
Well, I picked 2. The first one is The Magic Furnace by Marcus Chown, which I think I read when I was maybe in my final year or 2 at school, possibly my final year. And it's a book about how we discovered about atoms and how they interact in the periodic table and how that affects stars and how stars taught us about the periodic table and vice versa. And it opened my eyes to a lot of things I really didn't know about. I mean, I had done chemistry at various levels, and certainly the story of how we learned these things. Before that I hadn't known, and I really enjoyed hearing how people were faced with these mysteries and how they finally actually took strange things observed in different places and put them together. And actually that has a lot to do with how scientific method, and even today when we're trying to take that further and not just understand the structure of atoms, we're trying to understand fundamental particles much smaller than the atom. Actually looking back, that it's a very, very similar things that we're trying to do, taking different possible hints and things from different places and trying to build a consistent picture. So that was my first one, and the second one I read just before going to university, I think, and it was The Man Who Loved Only Numbers by Paul Hoffman, which is a biography of Paul Erdős, the mathematician, and it is just brilliant because it's an engaging story of a man who was an absolute genius but incredibly eccentric, and was only able to sort of do what he did in terms of maths because there were lots of people who were looking out for him, because he was completely unable to function in the modern world on his own, but just had a very unique way of looking at things and was a real genius and was able to solve many problems in number theory. And I was saying to you before that number theory, I always like number theory because a lot of the problems they're trying to solve are very, very hard to solve but can be stated very simply. So the average man in the street, you can, in 2 sentences, you can explain exactly what the problem is. Like the 4-colour map theorem, can you draw a pattern of blobs and colour them so that no two ones that are next to each other have the same colour? It sounds kind of simple, but actually it's not, and although it's proved, it was proved with a sort of brute force computational method in the end. And I just really enjoyed hearing the story of these results.
Yeah, that's amazing. Thank you for sharing that. And thank you for coming on the podcast. It's been absolutely brilliant to chat with you and to discover more about the life of a researcher and what you're researching currently.
Well, thank you very much for inviting me. I enjoyed it.
So thank you for listening to this week's episode of Delving into Academics, and I hope you found it interesting. Please like, review, comment and subscribe wherever you're listening to this. And if you want to find out more about the researcher, I will have their university website page linked in the description. See you in 2 weeks for another episode.